In this video, we will be discussing the last two methods of finding the time complexity of the code. The first method is using the memory model and the second method is using the function called tree. We are discussing them together because they are related. During the execution of the program, whenever a function is called, a memory is allocated to the function in the memory stack, and that memory is called the stack frame of the function. All the local non-static variables of that function are allocated memory in the stack frame of that function. When the function returned, the stack frame of the function is deallocated and that memory becomes free. If the function is called again, then a fresh stack frame of the function will be created and all the local non-static variables of the function will be allocated memory again. That's why you will see that every time you call a function, the local variables of the function are reinitialized again, whereas the local static variables of the function retain their values across the function call. Because static variables are not allocated memory inside the stack frame, you must have written the code to compute the factorial of a number. Mathematically, factorial of n is n into factorial of n minus 1 for all n greater than 1. And if n is equal to 1 or 0, then this number is 1. When we convert this mathematical definition into code, it will become a recursive function. Another way of looking at factorial of a number is n factorial is the product of all the numbers from 1 to n. So it will be 1 into 2 into 3 into 4 into 5 all the way up to n. This is an iterative way of looking at factorial of a number. If you convert this logic into code, then it will get translated into a for loop. Let us compare these two functions. The first function is a recursive function to find the factorial of a number, and the second function is an iterative function to find the factorial of a number. Let us say that this is the main function which is calling the factorial function. Let us see how it looks inside the memory when main function calls the first fact function, and then we will compare it with the picture of the memory when main function calls the second function. This is the area of the memory which is allocated by the operating system for the execution of this entire program that has two functions. First, the main function is called, so there must be a stack frame for the main function. Let's say this is the stack frame of the main function. The stack frame of main function will have one local variable x, but the value of this local variable x will be initialized by the return value of this factorial function. Therefore, this factorial function is called. So when the factorial function is called, this 4 goes to this variable n. The fact function also has only one local variable and that variable is n. This variable n will be initialized with value 4. What will this function do? This function will first check if 4 is less than equal to 1. Because 4 is not less than equal to 1, so it will call the same function. It will call the same function for n minus 1, that is 3. So when the same function is called, a new stack frame will be created, and in that stack frame the value of n is 3. These two stack frame belongs to the same function fact. It means that for one function there may be more than one stack frames of that function inside the memory. You can also look at it this way, that if there are more than one stack frames of a function inside the memory stack, then there must be recursion. Now what this function with n equal to 4 is essentially saying is that you call the function for n equal to 3, and whatever this function returns, it will just multiply that with 4 and return that value to the main function. Now let's see the function where n is 3. The function in which n is 3 will first compare 3 with 1 because 3 is greater than 1. So this function will also call the same function for n equal to 2, and whatever this function returns, it will then multiply that return value with 3 and then return it to the calling function. The same thing will happen inside the function where n is 2. It will first call the function for n equal to 1, and whatever this function returns, it will then multiply that with 2 and return it to the calling function, which is the function where n is 3. Now there are 4 stack frames of the same fact function inside the memory, and the topmost stack frame represent the function which is under execution, whose instruction is getting executed. In the topmost function, because n is equal to 1, this condition is true, so this function will return 1. When it returns 1, the stack frame will be deallocated. So I can rub it, but I'm just crossing it out. So crossing it out means that this memory is now free. Now the control comes to the function where n is 2. And what is the value being returned? The value returned is 1. At this point, this function will just multiply 2 and 1 and it will return 2 into 1, 2 to the function where n is 3. Now because this function also returns, the control comes to the function where n is 3. Inside this function, it has received the value 2 as the return value of the fact function, and 6 will be returned to the function where n is 4. And finally, this instance of the fact function will multiply 4 and 6 and return 24 to the main function, and the value of x will be 24. Let's see this code running inside Visual Studio Code. I'm using Java programming language inside Visual Studio Code. This function need to be static because we are calling it from main function, and I have put breakpoint so that the execution control stops at that point. Let's debug this. So I have started the debugging. This is the call stack. Inside the call stack, you will see, inside the call stack, you can see that there is this function main. So right now the execution is inside the main, and there is only one stack frame, that is of main. Now if I continue, then the execution will go inside the fact function. First there was only one stack frame of main function. Now we have two stack frame, one of main and one of fact. If you see the variables of the stack function, then you will see that there is one local variable n whose value is 4. If I continue it again, then it will stop inside the stack frame of the second fact function. Now you can see that there are two stack frames of fact function and one stack frame of the main function. Main function has called the fact function where n is 4, and this fact function has again called the fact function where n is 3. If I execute it again, if I continue it again, then one more stack frame of the fact function will be created where the value of n will be 2. Now we have one more stack frame of fact function. If I continue it again, one more stack frame will be created. So now we have 4 stack frames of the same function. The topmost stack frame has n equal to 1, second one has n equal to 2, third one has value of n as 3, and fourth one, which was called from the main function, has value of n as 4. And the execution is suspended in all of these stack frames. Now you can see that the topmost function will return the value 1. So the topmost function has returned the value 1. One of the stack frames is deallocated. The topmost stack frame is deallocated, and the execution control has reached the second stack frame, which has called the function with n equal to 1. Now inside this function, it has received the return value as 1, and the value of n is 2. So it will multiply 1 and 2 and return 2. You see, one more stack frame is deallocated now, and the execution control is inside the function where n is 3. So this will multiply 3 and 2. Now the execution control has reached the fact function where the value of n is 4. So this function has received 6 from the function that it has called, and now it will multiply that 6 with 4. It will return the product of 6 and 4 to the main function. So this value of x is 24. We can print it if we want. Let's talk about the time complexity now. We can say that the function is called n times, and every time the function is called, it will perform one condition check, then it will call the function again, and then it will perform the multiplication. There is one decrement also because it will be doing n minus 1. So one decrement also. So the condition check, the multiplication, the decrement, these operations are performed inside every stack frame. I mean, you can say that the topmost stack frame does not perform the multiplication and decrement, but we are talking about the order complexity, so we will ignore the constants. We can conclude that these 3 operations are performed order of n times. Because all of these 3 operations takes constant time, so the total time taken by this function is order of n, or big O of n. Now let's look at the execution of the second function. Let's assume that this is the memory which is allocated, and main is calling this fact function. If main is calling this fact function, it means that there must be a stack frame of the main function. Inside the stack frame of the main function, there is a local variable x. When this fact function is called, then the stack frame of this fact2, the name of this function is fact2, and here we have written only fact, so you can just correct it. This fact2 function is called. All the local variables of this function will be allocated memory inside the stack frame of this function. There are 3 local variables. First local variable is n, which will be initialized with 4 because this is what we are passing from the main function. The second local variable is product, which will be initialized with 1 because this is what we are initializing it with. And the third local variable is I, which will be initialized with 2. After the initialization, the execution of this function starts, and this for loop will be executed. Inside this for loop, product will be multiplied. So 1 into 2 into 3 into 4. And final value of product will be 24, which is the same as we have in the previous section. And this 24 will be returned to the main function. When this 24 is returned, then the stack frame will be deallocated. You may notice that in this case, there is only one stack frame but the size of the stack frame is bigger than the size of the stack frame in the previous recursive code. We will be talking about the extra memory that these two functions are consuming in the next section. In this section, let us focus only on the time complexity. So how much time is this fact2 function taking? Inside this fact2 function, because we have a for loop and we have seen that this for loop will take order of n time, because there will be n condition check, n multiplication and n increment. So we can say that even this function is taking big O of n time. Therefore, we can conclude that from the point of view of asymptotic time complexity, the first function and the second function are same, because both of them are taking time that is proportional to n. Both of them are taking linear time. What it means is that the first function is taking big O of n time. It means that the real time taken by this function must be some constant into n. And because the second function is also taking big O of n time, it means the real time taken by this function must be some other constant k2 into n. Now, if k1 is bigger, then the absolute time taken by the first function will be more than the second function. And if k2 is larger, then the second function is taking more time than the first function. So if the asymptotic complexities are same and we are doing a deeper analysis, then we may compare the constant factors of the two functions. And in high-end product companies, you are expected to have that kind of deep analysis knowledge. Let us look at the work done by the two functions again. Let me clean up all of this and then we will compare the work done by these two functions so that we can find the absolute time taken by these two functions and compare it. We will be looking at only the work done by the fact function and not the work done by the main function. In the first case, there are n function calls. We are writing it because every function call takes some time. So the time taken to create the stack frame of the function will be the time taken to call the function. Then there are n function return also. Whenever a function returns, some cleanup need to be done because the stack frame will be deallocated, the instruction pointer need to be shifted, the state of the calling function need to be reloaded. So all of these work need to be done when the function returns. All of these work takes some time. Therefore, we are considering that time. There are n function calls and there are n function returns. And then we have seen that there are n condition checks, there are n multiplications, and there are n decrements. You may refine it further and say that the multiplication and decrements are happening only n minus 1 times and not n times. But the condition check is happening n times. Now let's look at the second function. In case of the second function, there is only one function call. If you want to find the factorial of 10, then the first function will have 10 stack frames. But the second function will have only one stack frame. If you want to find the factorial of 20, then the first function will have 20 stack frames, but the second function will have only one stack frame. Therefore, the number of stack frames generated in case of the first function depends on the input value n. But in case of the second function, the number of stack frames is constant. There will be only one stack frame. So there is only one function call and there is only one function return. Now the work done by this function is the work done by only one instance of this function. There are n condition checks. Now you can say that the number of condition checks is not n because we are starting from 2. So number of condition checks is n minus 1. But I'm ignoring that small minuscule number. There are n multiplications also. Same goes for multiplication also because we are starting the multiplication from 2 and not from 1. And there are n increments also because we will be doing I plus plus. So here we are doing n minus 1, here we are doing I plus plus, here we are doing the decrement operation, here we are applying the increment operation. N condition check, n multiplication and n decrements are almost equal to n condition check, n multiplication and n increments. But in case of first function, there are n function calls and n function returns. Function call in itself is a very expensive operation and function return is also a very expensive operation. Therefore, the time taken by the first function is much more than the time taken by the second function, even though their asymptotic time complexities are the same. In absolute sense, the first function will take more time than the second function. As a thumb rule, you can remember that the recursive function almost always takes more time and it almost always takes more memory. We will discuss the memory part in the later section of this course. So this is how you can find the time complexity of a function by considering how many times the function is getting called and how many stack frames of the function are getting generated inside the memory stack. This was the memory model. Memory model is a technical term and function call tree is a non-technical term to represent the same. For example, if you denote the function call tree, then first the function will be called for n equal to 4. then the function will be called for n equal to 3, then the function will be called for n equal to 2, then the function will be called for n equal to 1 in case of the recursive function. So if we are writing it just like this without showing the stack frame and local variables, then we are drawing the function called tree. You notice that it's called a tree and not a graph because there is a parent-child relationship, and you cannot have a disconnected component. Let's look at the pre-order traversal function again. First, we will draw the memory model for this tree, and then we will use the function called tree to get to the same result. The first time when this pre-order traversal function is called, root must be pointing at the root of the tree. So if I draw the memory model, the stack frame of the function has root equal to a. I'm just writing root equal to a, which means that root is pointing to a. Because root is not equal to null, so it will print a, and then first it will call the same function for the left child of a. Left child of a is b, so I'm just writing b instead of root equal to b. So the function is called for b. Because b is also not equal to null, so this function will print b, and then it will call itself for the left child of b. Now the left child of b is null. This function gets called for root equal to null. When root is null, it will hit this terminating condition and it will just return from here itself. So the function gets called for root equal to null, and then it does nothing and just return. And the control comes back to the function where root is b. Now inside this function where root is b, we have already called the function for the left child. Now we will call the function for the right child of b. So when you call the function for the right child of b, the function will be called for root is equal to e. I'm just drawing the stack frame of e next to the stack frame of null. This indicates that the stack frame of e will be created at the same position where the stack frame of null was there. Otherwise, you can just rub this null and create the stack frame for root equal to e here. For the time being, I'm just leaving null as it is, and later we will see why we are doing this. So a calls the function for b, b calls the function for null, then null returns and the function gets called for e. Now first e will print itself, then e will call the function for null, which is the left child of e. This function will also return, then e will call the function for the right child of e, which is also null. So e calls the function for the left child, e calls the function for the right child. Both of them are null, so they will just return. Control comes back to e. E has checked this condition, E has printed itself, E has called the function for left child, E has called the function for right child. So everything for E is done. So this function will also return, and the control comes to the function where root is b. Now for this root equal to b, b is already printed. We have called the function for the left child of b, we have called the function for the right child of b. Therefore this b will also return, and the execution control comes to the calling function of b, which is the main function. So a calls b, b calls the left child of b, then this returns, then b calls for the right child of b, which is e, then e calls for its left child, this returns, then e calls for its right child, this returns, then finally e returns. Now because everything at b is done, so b will also return. Now a has printed itself and the left child of a is completely processed. Therefore, the function will be called for the right child of a, which is c. When the function is called for c, then c will first print itself. After printing itself, c will call the function for its own left child, which is f. Then f will call the function for its own left and its own right. The left child of f is null and the right child of f is also null. They will just return. So first the function will get called for the left child of f, which will just return. Then the function will get called for the right child of f, which will also return. Then the control comes back to f. Now f will also return, and the control comes to c. Then c will call for the right child of c, which is also null. Then this will also return, and c will also return, and finally a will also return. The final output of the pre-order traversal will be a, b, e, c. You may notice that the function is getting called for root equal to null a lot of times. Exactly how many times will the function will be called for root equal to null? If a binary tree has 1, 2, 3, 4 and 5 nodes, then there will be 5 plus 1, 6 null pointers in the tree. The left pointer of b is null, the left and right of e are null, the left and right of f are null, and the right of c is null. If you count, the total number of null pointers in this tree are 6. This is true for all n. If there are n nodes in a binary tree, then number of null pointers in the binary tree will be n plus 1. It means that the preorder function will be called n times for valid nodes, and the function will be called n plus 1 times for null values, because we are calling this preorder traversal function for all the pointers. Therefore, the total number of times this preorder traversal function gets called will be 2n plus 1. Because 2n plus 1 is order of n, so we say that the time complexity is big O of n. You notice that this is much more detailed than when we found the time complexity of preorder traversal using the element access method. And when we concluded that because the preorder traversal function is called for every node, therefore the time complexity of preorder traversal is order of n. That answer was correct, but this is a much deeper analysis. How do you draw the function call tree for this? The function call tree for this will be that first we call the function for A, then from A we will be first calling the function for B, then for C. From B we will be calling the function for null. Then from B we will be calling the function for E. From E we will be calling the function for null and null. From C we will be calling the function for F. From F we will be calling the function for two nulls, and C will call the function for null. You can see that the function call tree is actually very similar to the memory model. So if you flip this memory model upside down, then you will get the function call tree, and that is why we are discussing these two methods together. So function call tree is a less cluttered version of the memory model only. We have already seen in the previous section, you can go back to those sections where we found the time complexity of Fibonacci function using the function call tree method. This is the recursive version of the Fibonacci, and this is the iterative version of Fibonacci. To find the time complexity of recursive version of Fibonacci, we use the function call tree. So if you want to find the fifth term of Fibonacci, then first you will call the function for 4, then you will call the function for 3. To find the fourth term of Fibonacci, the function will be called for 3 and 2. Inside the function where n is 3, the function will be called for 2 and 1, and so on. We have already drawn this function called tree in the previous video, so you can go back and see that previous video and see how the function called tree for Fibonacci was designed. In most of the cases, the function called tree method will be used for piece of code where recursion is involved. But the memory model method comes very handy, not just to find the time complexity, but also to find the space complexity. In the next section where we look into how to compute the space complexity, we will be using this memory model method a lot.